conservation of linear momentum. Okay, what is meant by conservation of linear momentum? Principal conservation of linear momentum states that the total momentum is zero or constant, okay, if no external force acts on a closed system. Okay, so we need to look one by one. Okay, first of all, let us look at, he says that total momentum must be zero. Zero later I will talk, yeah. I will talk about zero later on. Okay, if we look at constant first, yeah. Total momentum must be constant, okay, provided no external force. So we can say there is no external force, yeah. External force is zero, and it must be a closed system. Okay, this is represented by this formula. Total initial momentum must be equal to total final momentum. But why we have initial and final momentum? Okay, this total initial momentum refer to the total momentum before collision. And this total final momentum is referred to the total momentum after collision. Look at these two balls. Okay, look at these two balls. This is happen before collision. Before collision, this is ball 1 is mass 1, ball 2 is mass 2. Okay, and before collision, M1 has velocity U1, M2 has velocity U2, and they collide. Here it collide. After that, mass 1 has final velocity V1, and M2 has final velocity V2. Okay, so here the total initial momentum, here it means, okay, before collision, the total momentum before collision, which is this one. That means if we total up M1 times M2, okay, this is a momentum. This is the initial momentum for P1, initial momentum. Okay, and we total up with the initial momentum for P2. Yeah, this is P2. If we total up these two, M1 U1 plus M2 U2, okay, the total initial momentum, okay, will be equal to the total final momentum, which is this one. That means the total final momentum, okay, which is M1 V1 plus M2 V2, which is this one. After collide, okay, after collide, M1 has final velocity V1, M2 has final velocity V2. So M1 V1, we will have the P1 final plus P2 final. Understand? So the total, okay, I just want to write here. This is the total initial momentum. This is the total final momentum. Okay, so I'm going to change to the color. This is the total final momentum. Okay, and these two, they are equal. Wrong again. This is the final momentum. So this initial momentum is the total initial momentum. That means M1 U1 plus M2 U1. The total initial momentum will be equal to the total final momentum, which is M1 V1 plus M2 V2. They are equal. Okay, so this is what it means by total momentum must be constant. Okay, the total initial momentum must always constant. That means no change of total momentum. The initial momentum before collision must be equal to the total momentum after collision. Okay, total momentum before collision must be equal to total momentum after collision. Okay, so you must remember, this is before collision and this is after collision, and both of them have the same momentum. Okay, the total momentum must be constant, or sometimes we say it as conserve. Conserve, from the word conservation, conserve. Total momentum is conserve. Okay, why he says zero? Why sometimes the total momentum is zero? This one normally happen during explosion. You know, this one normally happen during explosion. You know that like for example, like let's say I have you know, like a nuclear bomb. Like a nuclear bomb. Okay, like a nuclear bomb. Let's say it has two parts. Yeah, it has two parts. Let's say it has two parts with this one M1, this one M2. Okay, let's say. So suddenly explode. Suddenly explode. So this M1 will go this way. And then M2 will be separated and go the other way. Understand? Go the other way. Explode. So from here we can see this is before. This one is the before and this one is after. So before explosion, what's the total momentum? What's the total momentum? Total initial momentum is 0. Total initial momentum is 0. So after explosion, the final momentum must also equal to 0. Because this total initial and final must be equal. Maybe I don't draw like this. Maybe I draw. Okay, I draw better. Yeah. Maybe I draw like this. Here. Okay. So, the total initial momentum must be equal to total final momentum. Initially, before explosion, they don't have velocity at all. U1 is 0, U2 also 0. You see? U1 0, U2 0. So momentum also 0. The total initial momentum is 0. But after explosion, if mass 1 is going to the left, mass 2 must going to the right. During explosion, you cannot say if mass 2 going to the right, then mass 1 also go to the right. This one, the momentum does not conserve. If mass 2 is going to the right, the mass 1 need to go backwards, need to go to the opposite direction. That means one must be a negative value, one must be a positive value. Then when they total up, they will get 0. You understand? I can say total final momentum is we know it's M1 V1 plus M2 V2. So if this one is positive, this one must be negative. Then only they can be cancelled out to get 0. So to be equal to the initial momentum. So to be equal to the initial momentum. So if explosion, if one go to the right, the other one must go to the backwards. That's like a gun. Like a gun, pistol. Now I remember about pistol with a bullet inside. If before explosion, before you fire the bullet, the total initial momentum is 0 because the gun. This is the gun and this is the bullet. Both are not moving. But after explosion, you have the gun will experience a recoil speed. This is a V2, and then the gun will have a recoil speed V1. Okay, recoil. So V1 must be negative, V2 must be positive. So because why? Because we need to get a final momentum 0 be equal to the initial momentum. So the total final momentum is also M1 V1 plus M1 V1, M2 V2 we know that this one is negative, this one is positive. Cancel, you get 0. Because initially both of them are not moving. M1 U1 M plus M2 U2, both of them are 0. All of them are 0 0. So initial momentum is 0, but after that the bullet go forward, the gun must go backward. That's what we call recoil. The recoil speed. Yeah, turn backwards. Okay. This is what I see. What it means by explosion. This is what it means by total momentum must remain 0. Total momentum remains 0. Is for explosion. Okay. Or constant. If constant means already initially, let's say you have two billiard ball already moving, they collide. The total initial momentum must be equal to the total final momentum, must be constant or conserved. And before collision and after collision, they have the same momentum. M1 U1 plus M2 U2 equal to M1 V1 plus M2 V2. Okay, provided, but there is a condition, provided no external force acts on a closed system. Okay, what does it mean? What does it mean by this? And maybe I should just did all this. Okay, now I want to explain about this. This part. No external force act on a closed system. Must be a closed system. No external force. No resultant force is 0. Closed system. So, closed system, that means in reality you cannot, very hard to achieve a closed system. In reality, very hard to have no external force acting on this snooker ball or billiard ball, because there's always friction. You see that unless this no external force can only be achieved in the space. You understand? Because if a snooker ball on the table, snooker ball, they're sliding on the surface, on the surface, they experience friction. This one got friction. This one, the M2 also got friction. This one is external force already. This one already got external force. So this friction will surely slow down the velocity. Will surely affect the velocity. This friction also, friction experienced by this red ball will slow down the U1. The friction experienced by the mesh 2 also will slow down the U2. So this external force will surely affect the velocity, will affect the momentum. So this is not a closed system. This is an open system. You understand or not? Open system. So how to achieve really a closed system? I can say it's only happen in the space. In a space, whereas there no friction, no external force, no friction, no air resistance, then that is really a closed system. Okay. So alright, you understand? So a closed system is only in the space where there is no friction at all. No such friction at all. Yeah, no air resistance at all. Nothing. So just the two ball itself. Okay. We can say if it's only two ball with no air resistance, no friction, just these two ball. Okay. This is a closed system. Yeah. Like the gun. Like this gun. This one, the bullet and the gun. The bullet and the gun is one closed system. The total momentum of the gun plus the bullet is one closed system. The nuclear bomb is also one closed system. Okay, one closed system. Yeah, provided you are not sliding on surface, we know that any surface will have friction, isn't it? If got friction, means got external force, then it's not a closed system already, it's a open system. Okay. And, if no external force, we can say like, for example, no friction, no friction, no air resistance, yeah, air resistance. Okay, so that's it. Yeah, one thing, momentum is a vector. Remember that momentum is a vector. So it has what we call the direction. Okay, remember the direction again. And the direction. Just want to draw it out. Yeah. Remember the direction? I told you about the direction. Going upward, positive. Going right, positive. Downward, negative. To the left, negative. This is momentum. Momentum to the right, positive. Upward, positive. Momentum to the left, negative. Downward, negative. Momentum is a vector, so it has a positive, negative sign to show direction. And also, if two dimension, we need to resolve into components. Because why we need to resolve into components? Because we have direction. When we have direction in something, we always need to resolve into components. Why we suddenly talk about two dimension collision? Okay, why we have two dimension? Okay, before we learn about this, we need to look at this one. For collision, we have one-dimensional collision. We also have two-dimensional collision. You see that? We want to learn why we have two-dimension collision. That involve the conservation of linear momentum. Why we have x momentum and y momentum. Why we need to learn about two-dimension collision? Because collision, we have two types. We have one-dimensional collision. We also have two-dimensional collision. The one-dimensional collision has a name. It is named as head-on collision. The head-on directly collide. Head-on collision. Head-on, the word head-on means one dimension. Remember that. Head-on, if you see the question, it says it got the keywords head-on. An object experience a head-on collision with another object. Okay, the word head-on, this keyword head-on, means only one dimension. It only involves one component. Remember that. Okay. If involve two components, if the collision involves two components, x and y components, then it will give certain angles. Yeah, it will give certain angles, and that kind of collision we call oblique collision. Oblique collision is a two-dimension collision. It will have two components. Okay. One-dimension collision means only has one component. Okay, only one component. Two-dimension collision, it has two components. That means it will have x and y components. And because momentum is a vector, so when we want to solve conservation of linear momentum in a two-dimensional case, or the oblique collision, we need to resolve the momentum into two components to solve the question. We cannot directly use this formula. We cannot directly use m1u1 plus m2u2. We must resolve into components. You will have m1u1x plus m2u2x, and we also have m1u1y plus m2u2y. We need to resolve into components, okay, for two-dimensional case. Let us first look at these one-dimensional collision and two-dimensional collision. The reason why two-dimensional collision will have two components. This is the reason why. Okay, look at this. The definition of head-on collision and oblique collision. Oblique collision is also called non-head-on collision. Okay, Non-head-on or oblique collision is a two-dimensional collision. What's the difference of these two collisions? Head-on collision. Head-on collision is a one-dimensional collision. Okay, only involve one component. Why head-on collision only involve one component? Why? You see, head-on collision or one-dimensional collision means the velocity of each body just before impact is along the line of impact joining their centers. Remember, like this ball, we see this ball, this red ball and this purple ball. They collide head on. Okay, you see there is a line here. There is a horizontal line joining both centers. Do you see joining both centers? Maybe I draw it. Draw it. You see that? This is the center of the red ball, and this is the center of the purple ball. Center of red ball, center of purple ball. The horizontal line are joining their centers. You see that? Joining the center of red ball, joining the center of purple ball. This red ball and purple ball are moving along the line of impact, joining the center, and they collide head on. They collide head on. So as a result, this red ball will move in opposite direction. Purple ball also move in opposite direction. Only and one component. It only has one. Result in one component. They still move on the same line of impact. Because it's like center collide center. This is like center collide center. So as a result, the final momentum only have one component. It will have, let's say this is this is M1, this is M2, this is V1, this is final velocity V2. So it will be M1 V1 plus M2 V2. That's it for the final momentum. Okay, for the final momentum, it will have only M1 V1 plus M2 V2. That's it. Okay, but the thing is, for this two-dimensional collision, how it collide? What is mean by oblique collision? What is mean by two-dimensional collision? Oblique collision. Oblique collision means the velocity of each body just before impact is not along the line of impact joining the center. In fact, it's not joining the center also. What I can say is, not along. You see, these two balls, they are not moving along with the line of impact. I mean, the center not aligned with the line. You see the center of the red ball and the center of the purple ball. The center of the red ball and the center of the purple ball do not fall on the line of impact. Do not fall on the line of impact. So it's not center collide center. Yeah, it's not center collide center. They collide, maybe they collide at an angle. You see that? Like this, the red ball is over here. Hold on a second. This is the red ball, and this is the purple ball. Purple ball is over here. You see, they collide over here. They do not collide head on. They do not collide head on. This one head on collision. Maybe I should draw this one also. Collide head on means really head on. Really head on. Collide center to center. Do you see that? This one head on. Collide head on. Head with head collide. Head with head collide. They will result in one component. But this one is not collide head on. It's collide slightly at the side. Collide slightly at the side. Because why? Because the body, they are not moving along. Not moving along the line of impact. The line are not joining the center. The line are not joining the center. So they collide like at slightly at the side. So the result is these two balls, they will be after that they will be reflected in sideways. They will have angles in after collision. They will result in two components. They will become. It will have two components. It will have x. It will have let's say we have x, and we also have y components. It will have an x components. You see that it will have an x component and it will have y components. Remember, momentum is a vector. Momentum is a vector. It will have directions. Okay, it will have directions. Since you have direction, and if it involves two components, then you need to resolve the momentum into two components. Okay, so it will have angles. Like this case, it will have angles. So how to find momentum in this case? How to find the final momentum in this case? How to find the final momentum in this case? We cannot just m1 v1. Okay, this one, the red ball will have final velocity v1. The purple ball has final velocity v2. So is m1 u v1 plus m2 v2? Wrong. You cannot directly write like this. This one only for one dimension. This one only for one dimension. You see that this equation is only for one dimension. M1 u1 plus m2 u2 equal to m1 v1 plus m2 v2. This one is only for one dimension. If two dimension, you need to use this. You need to use this formula. If two dimension, you need to use this formula. If one dimension, use this formula. Remember, this one is only for one dimension. Two dimension, you need to use this formula. Okay. So you cannot use this for m1 v1, m2 v2 for two dimension. No. Okay. Instead, these two dimension, you need to resolve into components. You need to resolve into components. You will have v1x and v2x. So like for this one, for example, and remember, momentum, it has direction, positive, negative. Remember that. Again, this one, copy this one, and I want to paste over here. This one. Okay, so remember, like so we can say going to the right is positive, going to the left negative, going upward positive, going downward negative. Remember this one. And how to get let's say we know that this one is mass 1, this one is mass 2. So how to get the components? So the final momentum instead, this one is, we need to put m1 v1 x. Okay, no, you have two components. We have to do two components, x and y components. We will have total final in x, we have a total final in y. So total final in x, maybe you should resolve into components. You will have m1 v1 x plus m2 v2 x. Final momentum for y will have m1 v1 y and m2 v2 y. So we will, like for this case, we will have you have two components. You have x component and y components for v1, and then you have x component and y component for v2. Okay, we will talk about how to resolve this in the problem solving videos. Okay, I just want to roughly tell you that if two components, you have to resolve in two components, x and y components. Okay, that's it. You cannot use this one-dimensional. You cannot use the one-dimensional formula to solve questions for two-dimensional collision. Okay, you cannot use the one-dimensional formula to solve questions for two-dimension collision. Okay, for two-dimensional collision, you need to resolve into two components. You need to do separately. You need to do the x component and you need to do the y components. Yeah. So we have x component. We have total m1 u1x plus m2 u2x equal to m1 v1x plus m2 v2x. Y component also we have m1 u1y plus m2 u2y equal to m1 v1y plus m2 v2y. And we have direction. Sometimes this, remember this velocity, it will have positive and negative value. If this v1 is going to, let's say, going to the left, this one will become negative value. v2 going to the right will become positive value. This one, if v1 is going downward, going upward, let's say going upward, it will be positive. And this v2y is going downward, you have negative. Also sometimes the case, this one also maybe sometimes negative. This one, some the velocity, initial velocity sometimes also have a positive and negative sign. So remember, you also have the sign to represent the direction. So all these positive, negative, how to solve problems about the x component and y component, all I will explain in the problem solving videos. Okay, so that's it for this this video. Okay, let's move on.